Hello everyone, we are Group 3. My name is Zhe. Today, we are going to introduce antiferromagnet spintronics. Our final presentation contains 5 parts: introduction, 3 case studies, and a conclusion. The first case study is about room temperature magnetoresistance in all antiferromagnet tunnel junctions. The second is the piezoelectric strain-controlled antiferromagnet memory. The third is the antiferromagnet and ferromagnetic bilayer SOT. Okay, as a start, we will introduce basic antiferromagnetism. Antiferromagnet substances have a small positive susceptibility at all temperatures, but their susceptibilities vary with temperature. As the temperature increases, susceptibility increases but goes through a maximum at a critical temperature called the nil temperature. The substance is paramagnetic above nil temperature and antiferromagnetic below it. Below the nil temperature, antiferromagnetic substances tend to have an antiparallel alignment of magnetic moments, and the moments are strong enough to act even with the absence of an applied field, since the randomizing effect of thermal energy is low. The lattice of magnetic ions in the crystal then breaks up into 2 sublattices. The strong exchange coupling will exist and have a lower energy state when 2 sublattices make the spin align to the opposite direction. Therefore, an antiferromagnetic substance had no net spontaneous moment and only can acquire a moment when a strong field is applied to it.
Hello everyone, I'm Hong. Now, I will introduce some papers about the application of antiferromagnet spintronics. AFM spintronics is a potential candidate for high-density and ultra-fast information devices. However, the practical application is largely limited by small electrical output and room temperature. In this paper published by Nature, this group designed an antiferromagnetic tunnel junction with room temperature exchange bias effect. Let's look at this picture. This is the structure of common MTJ. From bottom to top is antiferromagnet, ferromagnet, tunneling layer, and ferromagnet. As for the AATJ, its structure consists of collinear and non-collinear antiferromagnet. And what is the difference between collinear and non-collinear antiferromagnet? It depends on how its spin direction align. If the magnetic moment can be counteracted each other along the z-axis, we call this kind of AFM as a collinear one. In contrast, if the magnetic moment can offset each other but not align on z-axis, it is the non-collinear antiferromagnet. For example, we image 3 vectors can form a triangle, and take these 3 vectors as the magnetic moment. That is, these magnetic moments will offset each other. So that is a kind of non-collinear antiferromagnet. And we can control the composition to get collinear or non-collinear antiferromagnet. For instance, MMPT is collinear, and if we add more magnets to MM3PT, it will become non-collinear AFM. Compared to the conventional MTJ, AATJ has much lower straight field, which means there is almost no disturbance between each AATJ, and it can increase the amount of AATJ in the unit area. That is, AATJ devices has the higher information density. However, while we can use all antiferromagnet, as the exchange bias system, because we can measure anomalous Hall effect from noncollinear antiferromagnet. This structure can behave like ferromagnet, hence it is similar to FM exchange bias system. And what is anomalous Hall effect? The left-hand side is the ordinary Hall effect. If we apply current and magnetic field, it will induce the Hall voltage. Compared to the ordinary Hall effect, anomalous Hall effect doesn't need to apply external magnetic field. The Hall voltage is induced by the intrinsic magnetic moment inside the material and cause accumulation of charge. The magnitude of anomalous Hall effect is positively correlated with the number of magnetic moment inside the material. By AHE, the noncollinear AFM can be treated as ferromagnet. Moreover, it makes AATJ can obtain the TMR ratio. Let's look at this figure. It shows AATJ has almost 100% TMR ratio at room temperature. In conclusion, this paper used the antiferromagnet tunnel junction to get a similar effect of conventional MTJ. AATJ not only has higher information density, but also has high TMR ratio at room temperature. This result makes AFMs more practical to use in real application.
Hello everyone, I'm Jin Lin. The work I'm going to report is piezoelectric strain-controlled antiferromagnetic memory insensitive to magnetic fields. And first, the piezoelectric material they used is PMMPT. Its chemical formula is shown here. It has a perovskite structure where the lead atoms located at the A site is H, and magnesium, neodymium, titanium occupy the body center B site. And oxygen atoms located at the face center. From the XRD pattern of the PMMPT, we can see that the black one is without the electric field, and the other two are with the electric field. So it's apparent that the electric field will create a strain on this PMMPT. And the antiferromagnetic thin film in this case is manganese platinum. It's a collinear AFM. We first check the magnetoresistance of this manganese platinum and the PMMPT drop structure. There are two configurations. The first one is the intrinsic property of the manganese platinum. The structure is in figure A, and the 4-point probe was placed on top of the manganese platinum thin film. The external magnetic field was exerted at certain angle with respect to the manganese platinum film. The result is in the figure B and C. It's clear that the large parallel or normal magnetic field only causes the 0.01% change in the resistivity or the resistance of the manganese platinum. And when a gate voltage is applied perpendicular to the structure, we can clearly see from figure E, the resistance has 2% change when the positive or negative bias was applied. And figure F is the corresponding polarization switching curves of the PMMPT. So for this, the electroresistance modulation is unlikely due to the electrostatic carrier injection, because a negative gate voltage should correspond to an increase of the resistance of manganese platinum in this measurement configuration. However, the measured resistance was low at a negative electric field. They also did the simulation. It turned out that the strand had almost no change on the band structure and the density of states of the manganese platinum. So they made further comparisons. Figure A is the hysteresis loop of PT, copper iron, PMPT, and gold. And figure B is the hysteresis loop of the PT, copper iron, and manganese platinum, PMPT. We can clearly see that there is a strong exchange coupling between the copper iron and the manganese platinum. And there's no exchange coupling in this case. So we can deduce that indeed the strand changes the magnetic properties of the manganese platinum. And this concept is visualized in figure C and D. When there is no strand on the PNPT, manganese platinum film has its original spin configuration and is at a high resistance state. When an electric field is exerted, a strand is created, and the strand helps to rotate the spin of the manganese platinum to be in the one direction. And this helps to enhance the exchange in coupling between the copper iron and the manganese platinum. So in other words, the strand rotates the antiferromagnetic spin axis of 101 oriented grains in the textured manganese platinum films, leading to the enhanced exchange coupling with copper iron and to have the low resistance state. They also examined the stability of manganese platinum and PMPT heterostructure. And the saturation resistance and the corresponding electric field was first identified in figure A. Then an external magnetic field was applied between these two resistance states. We can see from figure B, the resistance at high and low resistance states did not change under different magnetic field. Next, the device was tested for 10 days in air with a daily temperature variation of 3 Kelvin. The resistance state was stable with only 0.05% fluctuation. And this is much smaller than the commonly reported 1.66%. In addition, they applied an out-of-plane pulse field up to the 60 Tesla to the low resistance state and observed a resistance variation of 0.1%. And these results indicates that the information in this memory device was not destroyed even by a 60 Tesla magnetic field. So in this paper, they demonstrated using the piezoelectric material PMMPT to modulate the resistance of the manganese platinum antiferromagnetism film. They reported the AMR ratio of this device can be roughly 9%. The device is robust because it was not affected by the external magnetic field, and it had good stability under ambient conditions, and it is suitable for the low power consumption and high density memory device in the future.
I'm going to introduce an antiferromagnet-ferromagnetic bilayer system. For the structure, a ferromagnetic copper-nickel multilayer is deposited on top of an antiferromagnetic platinum-manganese layer. We can see the MH loops here. For the thickness of platinum manganese equals to 6 and 8 nanometer respectively. It shows that exchange bias in the positive X direction exists to break the symmetry with the thickness larger than 7 nanometers, whereas below this thickness it is effectively 0, which shows no exchange bias in the X direction. For the hysteresis loops below, there are loops for hole resistance versus channel current obtained under various exchange bias for the thickness of platinum manganese equals to 6 nanometers and 8 nanometer respectively. For the left one, no loops is observed at exchange bias equals to 0. However, for the right one, the boundary between the clockwise and anti-clockwise loops moves to minus mini-Tesla owing to the exchange bias. So we can find that only when the thickness of platinum manganese layer is larger enough that the field-free switching can be performed. In this structure, platinum manganese serves as the exchange bias source as well as SOT source. Thus, field-free SOT switching of the perpendicular magnetized ferromagnet can be achieved. The authors also showed in a later study that proper engineering of the stake structure, such as changing seed layer below platinum manganese from platinum to ruthenium, and inserting a platinum layer between copper nickel and platinum manganese, can result in an enhanced PMA and enhanced exchange bias and reduced switching current density. As you can see, the hysteresis loop on the right hand side shows that the increase in the amount of current flowing into the AFN layer effectively reduces the required channel current needed to switch the magnetization of copper nickel layer. Also, the increase in the amount of current flowing in the copper nickel layer allows higher switching amplitude of the hole resistance. It was also found that by engineering the exchange bias in the system, the stake can show a memristor-like behavior and thus find applications in neuromorphic computing. If we measure the hole resistance and channel current loops, we can find that the hole resistance is determined by the maximum channel current, resulting in intermediate resistance states. These intermediate resistance states are found to be stable even after turning off the current, which indicates that AFN-FN bilayers is a promising building block for artificial synapses in artificial neural networks. And the reason why it can have the property of gradual change of hole resistance is according to the single spin ensemble model, which explains well the exchange bias of polycrystalline systems. Look at the figure below. The bias direction of individual grains are random, and the aggregation of the grains exerts an unidirectional anisotropy in a collective manner. When a channel current is applied, we expect that all the grains lead to the SOT switching. However, the grain boundaries with different bias directions interrupt the domain wall propagation across the crystalline grains. Thus, the reversal is confined in a unit of crystalline grain as the channel current increases, and eventually the intermediate resistance states may be stable.
Okay, in conclusion, I'll talk about some characteristics and problems about antiferromagnetic materials. After that, I will discuss about how we apply AFN into SOT devices. Finally, I will mention some other applications about AFN in addition to the SOT devices. There are some properties for AFM materials. First, we already know that there's no net magnetic moment in bulk material because the moments nearby will align in opposite direction and cancel out the magnetization. Second one is that AFM have weak response to magnetic field and that it can give a better stability under field exists, which make it easier to be more stable in their state and is helpful to the data storage. Third one is that AFM has fast spin dynamics due to the strong coupling between moments inside, and this characteristic can be used in high-frequency devices. Last one, but I think is the most important one, is there's no stray field at AFM, which means AFM material won't create additional field to interfere other devices. Sometimes it may also show the impact from external field. In high-density circuit, it may be important to prevent interfere with each other devices. However, there's also some problems when using AFM material. First one is that it's hard to read due to its zero net magnetization, and it's difficult to be polarized. In AFM devices, the TMR ratio is quite low in room temperature, where we can only get small signal output. However, in case 1, we mentioned is to replace FM layer to non-collinear AFM material to form the junction we called AATJ, which we can get TMR ratio approach 100% in room temperature. Second problem is, although we know that it's more stable than of AFM material than traditional ferromagnetic devices, but it may have data loss under high temperature or under high magnetic field. Or in contrast, we need to put more power consumption to stabilize storage. So to solve this problem, in case 2, we introduce a piezoelectric strength control AFM memory, which the data storage can be stable even under 60 Tesla magnetic field. Last one is the problem when we use AFM into SOT devices. We know in SOT devices, the most important parameter is spin hole angle. However, AFM materials' spin hole angle are not so large compared with heavy metal. There's one way to improve this problem, which is to dope some heavy metal such as platinum or titanium into AFM. Then we can have larger spin hole angle with the advantage of AFM material. Then how can we put AFM into SOT devices? The main idea is to replace heavy metal layer by AFM and have better properties. Sometimes we can also change FM layer into AFM material, just as we mentioned in case 1. When we change the AFM into heavy metal, there are 2 effects we can see. The first one is exchange bias effect. In AFM bilayer systems, the top AFM atoms may have strong coupling with the bottom atoms of ferromagnetic layer and make it a preferred magnetization. This exchange bias effect of the AFM can achieve magnetization reversal of the ferromagnet layer without the need for the external magnetic field. This means that AFM can exert an internal effective field to FM, which is required for SOT and is difficult to heavy metal. Second one is why some AFM can replace heavy metal in SOT. Some AFM may exhibit a direct spin Hall effect. Then it can convert pure charge currents into spin currents. For example, in left figure is SOT device, use PTMN as spin current generation layer. And right figure, we use the IIMN as the spin current generation layer. In AFM systems, we may see the behavior similar to memristor can be achieved, where the magnetization reversal can be controlled in an analog manner. This shows that AFM systems are not only suitable for SOT devices, but also suitable for the neuromorphic computing. So let's talk about some other application to AFM. First one is neuromorphic computing. The bilayer system can be designed to be similar to the structure of human brain synapses. So we can, by adjusting the interface exchange bias to control the change in the magnetization direction, the storage and processing of analog signal can be achieved. And second one we call magnonics. In magnonics, the spin wave devices use magnets to transmit and process information. And it's ultra low power information technology. With AFM material, we can propagate spin waves much faster than the traditional FM materials due to its faster spin dynamics we mentioned before. And the third one is quantum computing. This is mainly talk about the control and operation of quantum bits, also called qubits. And because AFM has no magnetization, and so it can form stable quantum state for this application. So that's our report. Thank you for your attention.